Welcome back to Unit 5. In this lesson, we're going to learn how to Eulerize or semi-Eulerize a graph. The idea of Eulerizing a graph is very simple. We have a graph and we would like an Euler path or a circuit, but it doesn't exist. What we'll do to fix this is we're going to add duplicate copies of edges at odd vertices so that all of the vertices are even. Once all of the vertices are even, we know that there will be an Euler circuit. Let's take a look at this graph as an example. Each odd vertex is marked with a red dot. The other vertices have degree 2 or 4, so they are already even. Look what happens when I add a duplicate edge or a multiple edge between vertices B and C. By connecting two odd vertices, we now have two even vertices. They each have degree 4. We can do the same thing at the other pairs of odd vertices. Now we have a graph with all even vertices, so we have an Euler circuit. Knowing that we have an Euler circuit means that we can start at any vertex that we choose, and we can traverse the entire graph and end up right back where we started. Let's start here at vertex J. That will also be where we end. There are many different circuits we could create. I'll show you one example. If I start by traversing these three edges, notice that I do not want to go back from vertex I to J. If I do that, I'll be stuck and I can't traverse the rest of the graph without crossing over one of the edges a second time. In this case, edge JI is a bridge between where I haven't been and where I need to be, so I don't want to cross it when I have a choice. Let's instead head over to vertex H and keep going. Notice here at vertex L, I have these multiple edges between L and K, and I need to traverse them. You might initially think that we're stuck, but with those two edges, we can go to vertex K and right back to L. We have the same situation with the multiple edges between vertices B and C. And there we have our Euler circuit. Following the numbers 1 through 28, we can traverse the entire graph beginning and ending at vertex J. Let's head over to our security guard problem and our mail carrier problem. We'll use this method to help us out. Here's a simplified version of the graph that we have already drawn to model the security guard problem. Let's review this problem and see what we need to do. The security guard's assignment is to sweep on foot the entire neighborhood. His starting point is the corner of Elm and J Streets across from the school, and this is where he will park his car. This intersection is marked with the S in our graph. At the end of his patrol, he needs to come back to pick up his car. Now that we've learned so much about graphs, we recognize that what's needed here is an Euler circuit. Let's take a look at our vertices and see if we can find any with odd degree. Since we have odd vertices, we don't currently have an Euler circuit. But we can Eulerize this graph and add duplicate edges to create the best option for this security guard. What we'll need to do now is connect pairs of odd vertices with duplicate edges. Now every odd vertex has been connected to another odd vertex with a duplicate edge. This makes each odd vertex now an even vertex, and we have an Euler circuit. Beginning at S, here's one way that the security guard could traverse this neighborhood. But you could go a whole number of different ways and sweep this neighborhood with an Euler circuit. Notice that this still will require that the security guard does double back on some of the streets and walk them twice. But by Eulerizing this graph, we know that we have the least number of double backs needed in order to traverse this neighborhood. Now let's take a look at the mail carrier problem. Here's the graph that we created to model the mail carrier problem. I've simply removed the background. Remember that this mail carrier needs to start and end at the post office. We also drew in a lot of multiple edges already to show the streets that the mail carrier needs to walk both sides of. Those are the streets with houses on both sides. Take a second and look at all of the vertices. See if you can find any odd ones. Hopefully you notice pretty quickly that they're all even. With all of these multiple edges, we already made the vertices even. That means we don't need to Eulerize this graph. It already has an Euler circuit. I will leave it as an exercise for you to start at the post office and create an Euler circuit that travels the entire neighborhood over every edge exactly one time and comes back to the post office. Semi-Eulerizing is very similar to Eulerizing a graph. We're going to again add duplicate copies of edges at the odd vertices, but this time we're going to add edges until there are exactly 2 odd vertices. Let's try out this method with the Madison County problem and the UPS driver problem. Here's the graph that we drew to model the bridges of Madison County. Let's revisit the details of this problem. There are 4 islands, A, B, C, and D, and there's 11 bridges joining the islands to both banks of the river, the left and the right. Each time an out-of-town visitor crosses a bridge, they have to pay a toll of $25 called a maintenance tax. A photographer is hired to photograph each bridge and must cross each bridge at least once with as few recrosses as possible. The photographer can start on either bank of the river and end on either bank of the river. Hopefully it's clear why we don't want to go back and forth across these bridges. That would get expensive very quickly. But driving over these bridges, the photographer doesn't need to start and end back at the same location. He can leave the area from either bank of the river. Let's take a look at each vertex and see which are even and odd. Looking at vertex R, we have 5 edges that meet at R, so it is odd. Vertex A is even with degree 2. Vertex C is even. Vertex L is odd with degree 5. Vertex D is odd with degree 3. And vertex B is odd with degree 3. Remember that the photographer wants to start on one bank of the river and end at the other. Let's suppose that he starts at R and ends at L. This means we want an Euler path. We want to leave R and L odd. We do, however, need to add a multiple edge between vertices B and D to make those vertices even. With exactly 2 odd vertices, we've now semi-Eulerized this graph and we have an Euler path. Here's one way that the photographer could make their journey from R to L. Let's take a quick look at the UPS driver problem. Here's a simplified version of the graph that we drew to model the UPS driver problem. Let's review. A UPS driver must deliver packages around the same neighborhood that we had for the mail carrier and the security guard. However, they will enter at one point and end at another. They also have to go to certain homes where packages are delivered. Lastly, they don't have to traverse a street twice, even if there are homes on both sides, because they can simply cross the street on foot. For this example, we need an Euler path, not an Euler circuit. We will start and end at 2 different vertices. To have the most efficient route for this driver, we want to add as few extra edges as possible so that he can drive the minimum distance required to still traverse this neighborhood. We will leave our start vertex and our end vertex odd and make all other vertices even. Let's go through and mark all of our odd vertices. Starting with this vertex, notice that there's not another odd vertex right next to it that we can connect to. So we will need to draw 2 edges and connect it to the next nearest odd vertex. Notice that this will make both of those odd vertices even while keeping the even vertex in between also even. Next, looking at this odd vertex, we will again need to connect it with 2 edges to the next nearest odd vertex. And we'll continue in this way. Now we have semi-Eulerized this graph. We've made all but 2 odd vertices even. I will leave it as an exercise for you to map out the Euler path from start to end. And that will conclude this video lecture on Eulerizing and semi-Eulerizing graphs.